Hi everyone, my name is David Bach. I'm an environmental lawyer in Las Cruces, New Mexico, and I took the CS50 online class just as a way to develop some skills, technical skills that I can use in my practice. My final project relates to some of the work that I do in environmental law. It's called Using Extreme Gradient Boosting to Predict Ozone Exceedances in El Paso, Texas. And there's my information there. Um, so ozone pollution is a harmful air pollutant that's regulated under the Clean Air Act. It is not emitted directly from industrial activities, but instead forms when nitrogen oxides, or NOx, react with volatile organic compounds, or VOCs, in the presence of sunlight. And EPA has set a standard, a health-based standard, and under that standard, if an area has an average ozone level exceeding 70 parts per billion over an 8-hour period, then an exceedance has occurred. And this chart over here shows that the El Paso area has frequently exceeded that standard in recent years. So in this project, I tried to look at what other researchers have done using machine learning to predict pollution levels and to try to implement it for my region in particular. And I actually got this data science book here to read a lot about these different models to try to figure out what might be the most helpful approach for the input parameters that I have in this type of problem. And I also read several different studies that have looked at different machine learning techniques from artificial neural networks, k-nearest neighbor, and then I use extreme gradient boosting. But there are different ways you can try to implement this type of program. So the first thing I did in this project was just to gather my data. The Texas Commission on Environmental Quality has all of the pollution and meteorological data for the Chamizal air quality monitor in El Paso. So I downloaded all of the relevant data that I thought I wanted to look at and in a CSV file, and then I did some processing on that on those files to address missing values. As you can see, this is just an example, but as you can see, there's certain ID n equals 17, things that are not actual measurements that are included in there. And so I used an imputation approach where I simply used the neighbor, average the neighbors, the hour before and the hour after to impute the missing value. Then once I cleaned up the data, I first tried to predict this with k-nearest neighbors, which is a pretty simple machine learning technique that just relies on the assumption that points that are close together on a graph will be classified the same way. Here the graph is multidimensional that looks at all the different inputs, meteorological and pollutant inputs, and whether we've classified it as an exceedance or a non-exceedance day tries to predict based on where a data point falls relative to other data points that have already been classified. And this is the Rolling Stones and their video for the song Neighbors. That's why they're there. So this model struggled because exceedances are quite rare. You only have, even in a relatively polluted area like El Paso, you only have 8, 10, 12 per year. And so this model just defaulted to being very conservative because it realized that it was very likely to be correct if it just predicted non-exceedance pretty much all the time. Even with a lot of different tweaking, I ended up with a very low true positive rate, meaning I was very rarely correctly predicting exceedances. So then I switched to XGBoost, or extreme gradient boosting. This is an ensemble machine learning method that uses gradient boosted decision trees. So it creates decision trees in sequence, and then each new tree is trained to correct the error of the previous tree. So it looks at the gradient of the loss function, basically trying to see in which direction it needs to move the weights for the parameters to make the error a little bit less. And so you do this over a certain number of trees, and the parameters are something that can be edited to try different things. I used 100 trees in this uh, run. And I in my write-up that I did, I talk a little bit more about some of the other hyperparameters that I modified, including the learning rate and the depth of the trees um, in creating this model. So when I first ran this model, um, I still had some issues with a pretty low precision rate in terms of not, the model was basically erring on the side of being very conservative. Again, because exceedances are rare. And so the first thing I did was just to try uh, to weight the exceedances more highly in the formula in the algorithm using the scale POS weight parameter of the model. Um, but even that didn't seem to really get me very high. It was better than the nearest neighbors, to be sure, but I was still getting something like 38% correct predictions of exceedances, which is not high enough to be useful. So then I looked into using the synthetic minority oversampling technique. So what this does is it basically accounts for the relative rarity of the event of interest, which here is the exceedance days, by adding new data to the data set that is similar to the characteristics of the existing exceedance days, but not identical. So you have some new additional data points in the mix that the machine can learn from. So after implementing SMOTE, the synthetic minority oversampling, in the XGB classifier model, at the threshold of 40%, I achieved really good results. A true positive rate of 98%, meaning that more than 98% of the exceedances were correctly identified as exceedance days, and a true negative rate of 91%, which is still pretty good, which means that uh, it was still correctly identifying most of the, a large majority of the non-exceedance days as non-exceedance as well. We swept through different thresholds here. Again, on the assumption that because it's a pretty rare um, occurrence, we should sort of, in our results, assume that that we might need to boost the results a little bit to err on the side of treating something as an exceedance. So if the model said it's a 40% chance of being an exceedance, we said, and in the bolded there, we said it is an exceedance. So giving it a little bit of additional boost. So we ended up with a really accurate and precise model for predicting ozone exceedances at this particular monitor in El Paso, which could be useful in and of itself in terms of implementing public health strategies. If you know that the next day is likely to be an ozone exceedance, you can tell people to stay out, not to exercise outside, high risk individuals not to exercise outside on that day, and so forth. There's a lot of additional things I would like to do, but I would want to get my project done so I can have the credential. But I might do this anyway. A lot of other things to do, and trying to explore how other parameters might affect the model. Other pollutants that I didn't look at here, either because I didn't have the data, like VOCs, I don't have the data for this particular monitor, but other monitors do, or because generally they're not thought to be as closely correlated to ozone levels. They don't directly react with any of the precursors like sulfur dioxide and particulate matter 2.5. Although some of the studies I read did say there was surprising high correlation for some of these, and the authors weren't really sure necessarily why, but studying it more could cause us to, to think more about how some of these interactions occur in the atmosphere. And then the next thing that would be really helpful is that we have parts of our region that do not have any monitors at all for ozone, but may have monitors for some of the inputs. And so if we could use this model that we've trained on in an area where we do have ozone monitors, and then we applied it to an area that doesn't have ozone but has the others, we could say, hey, we don't have, there's no monitor here, but we know that you're having probably having 10 exceedances a year based on how these other inputs react in other parts of the region. And so that would be really helpful for regulatory strategies to say, even in this rural area, like in the middle of the Permian Basin, where there's quite a lot of oil and gas activity, but they don't have any ozone monitors, being able to say, well, based on what we've seen in other areas, this area is likely to experience ozone exceedance as well. It could be very important for developing regulatory strategies. And the final thing that could be done is that, to keep things simple, I just asked the model to learn whether it's an exceedance or not. But it could also be trained to actually try to say, well, the exact value of ozone on this day is probably going to be, 75 parts per billion because, or whatever, because the differences between an exceedance that's close to the threshold versus one that's very high above the threshold can also be very important for public health reasons.